Hey, it's Mr. Brooks here. We're starting our next chapter on circular motion. So far in this class, we have talked about objects moving in a straight line, but what happens if they are spinning, like the top you see in the picture, or anything rotating in a circle? How do we account for velocity, acceleration, and forces if it's going around and around? So that's what we're talking about in this next chapter. So follow along and listen as we go through it. Here's this picture that we have seen before. You have an object spinning around, a ball spinning around attached to a string. As it spins and spins, the string suddenly snaps. Which direction does the ball go? Well, if you remember Newton's laws and his first law, you know that it's going to continue in a straight line tangent to the circle. Knowing that, then we could ask the following questions. Why does the ball continue to move in a circle? What causes the ball to move in a circle instead of the straight line? And is the ball moving in the same direction? Let's look at the first one. If it moves in a circle, then there has to be an outside force. What is that outside force? Well, in this case, it's the string attached to the ball. Now, there's a more general term for that, and we call that the centripetal force. And you're going to be hearing that a lot in this next chapter. That same answer could be used to what causes the ball to move in a circle instead of a line. And is the ball moving in the same direction? Well, no, because it's going in a circle, it's constantly changing its direction. If it changes its direction, then we know it's changing its velocity, therefore it's accelerating. Before, we had everything traveling in a straight line. We measured speed as meters per second. It's how far it went in a given amount of time. But now with circles, you have to switch it up to revolutions in a given amount of time. So it would be like 3 revolutions per second or 5 revolutions per minute, RPM, something you guys might have seen on your parents' car next to the speedometer. An example of this, of how fast the edge of the tire would be, is the problem here. It has a radius of 0.29 meters and is rotated at 830 RPM. Then what is the speed at the outer edge of the tire? Well, we could use our previous formula, velocity is equal to distance divided by time, but we have to change it up a little bit because the distance is no longer a straight line. The distance is the circumference around the circle, which we know is equal to 2 pi r. So we replace distance with 2 pi r and we get the equation, velocity is equal to 2 pi r divided by the time. You plug in your numbers, and the answer is the outer edge of the tire is traveling at 25 meters per second. Like I said before, if it's constantly changing its direction, then its velocity is changing because velocity is a vector which is dependent on the magnitude and direction. So by changing its direction, we have an acceleration. If we have a change, or if we have a change in the velocity, we have an acceleration, and in this case, we're calling that acceleration the centripetal acceleration. And that equation is your velocity squared, your centripetal velocity squared, divided by the radius of the circular path. And if it's accelerating, we know by Newton's second law, there has to be a force to it. Force is equal to mass times acceleration. We call that force the centripetal force, or center-seeking force. It always points to the center of curvature. Now this might be a little bit different than the feeling that you get, and we'll talk about some misconceptions there shortly. But in the picture, as the car goes around, you have a force that's going to the center. In this case, it's the force between the tires or the force of friction between the tires and the road. Other examples of a centripetal force, you can see at the bottom, the string, like in the example before. You have a gravitational pull, and then the friction like you see in this example. You might have heard of this thing called the centrifugal force. The centrifugal force is a made-up force. Some people call it a centrifugal feeling. What it is as you rotate around, there's this feeling that you are being pushed to the outside. Again, since there isn't an actual force there, it's made up, but it's still given the name centrifugal force. We deal with the centripetal force, which is an actual force. Here's an example to help clear things up. If you're driving in a car and you make a hard right turn, you feel as though you are being pushed to the left side of your car. That's that centrifugal feeling of you being pushed to the left side. But in actuality, the left side of the car is pushing you, and that's that centripetal force always pointing to the center. Speaking of the centripetal force, here's the formula. Centripetal force is equal to your mass times velocity squared divided by the radius. Now, if you remember Newton's second law, you know that force is equal to mass times acceleration, so you might be scratching your head at this. But if we compare the two, your net force, and we set it equal to your centripetal force, we know your net force is equal to your mass times acceleration, and we know that the centripetal force is equal to your mass times velocity squared over the radius. So what's the difference? Why is there a velocity squared over the radius? Well, if you look to about 3 slides previous, we know that the centripetal acceleration is equal to v squared over r. So that's where you see these variables come in. So it's still mass times your centripetal acceleration. We take the centripetal acceleration and we substitute the v squared over r for that. An example problem that you might see on your test. Imagine you whirl a 1 kilogram rubber stopper attached to a string on a 1 meter radius circle. At 2 revolutions per second, what is the centripetal force on that stopper? You want to first change 2 revolutions per second into meters per second, because that's what we are used to working with. So to do that, it's 2 times your circumference, 2 pi r. We know the radius is 1 meter, so it's 2 times pi times 1 meter, and you get 12.6 meters per second. And then you plug those numbers into our force formula. Our mass is 0.1 kilograms. You multiply it by the velocity you just found, square it, and you divide it again by that radius of 1. Final answer is 15.8 newtons. I hope this made sense. If not, please ask either me or Mr. Mel. We'll clear up any misconceptions for you, and enjoy the rest of class.